Good afternoon, everyone. Our guest today is Lieutenant Commander Sam Greenaway. He is currently the executive officer on the Hassler. He graduated from this institution with a master's in ocean engineering in 2010, so a little before my time. He has a physics degree from Brown University, and he was recruited into the NOAA Corps in 2004. Someone is not muted. I hear someone else clearing their throat. Okay, sorry. Without further ado, let's make sure that no one else can.
It was.
So yeah, he's the executive officer now on the Hassler, and he's going to talk about their first year of survey operations and where he's collaborated with CCOM and sort of future collaborations with us. So let's welcome Sam.
All right, thank you, Ashley. And thank you all for the invite to come here and give this presentation. Hassler's been up at our home port. It's been our home port for a long time, but we've only been here since September. And it's great seeing some of the tendrils, the first tendrils, I think, of the collaboration that was really the genesis behind, or one of the big ideas of getting the boat home ported up here, start. And that's where I'm going to end the presentation as well, of where we have been collaborating and some things that we're struggling with that we certainly hope to get future help from you guys. This certainly does not trump the official guidance that's given to you on an annual basis from the Office of Coast Survey, but just some things that we're thinking about out in the field. It's also great having folks that are working down at the on the pier stop by and say hello, and just even that collaboration of just bumping into Tom Littman working on the sea bass down there and looking at, well, how are you doing RTK? And so that's been real terrific, and it's great having folks stop by, and like Tom Weber and Xavier stopped by earlier in the week and looked at some of my graphs and said that ain't right. So that's always good. It's good to have that. It's good to have I think some of the attitude that comes with from a research institution as well. When Ashley asked me to send my very late bio and abstract, which I finally got to early in the week, she said, "Well, what's your title?" And of course, me being 3 years now back into the out of academics, I said, "Well, of course, it's Lieutenant Commander Samuel F. Greenaway, NOAA, Executive Office, Ferdinand R. Hassler." She said, "Yeah, that's nice and all, but what's the title of your talk?" So I'm here to talk about the Hassler. So there she is. That's a picture taken yesterday. We were out running around with the rescue boat, enjoying the nice weather. I'm putting her up in the davit, getting ready to sail for a season. So in putting this talk together, what I kept coming around to, and I think what you guys would be interested in is, okay, so you got this goofy ship. Why'd you build it that way? And is that a good way to go and do survey? Is that a good thing when I go back to my home office, or when I'm asked to, hey, we're thinking about doing this, should we do it? And so hopefully I'll address some of the issues. And I think the answer you keep coming back to, as with many things in both hydrography and life, is, well, it depends. And there's a bunch of trade-offs between, well, if you optimize this, well, you lose a bit of that, or if you do this, you do that. So hopefully I think that's the theme that I'll probably keep coming back to, is what are some of the trade-offs when we make this decision? What do we have to pay for down the path with it? So here she is. Here's the mighty Hassler. She was just commissioned almost 2 years ago. Construction started many years ago. She's had a bit of a troubled birth, but she's now fully operational. So first off, it is a catamaran, 2 hulls, right? And looks probably, this is our sleekest angle. This is us transiting north through the Cape Cod Canal on our way here last September. But she's not a bunch of things that you think of when you think of catamaran. She's certainly not lightweight. She's not very fast. We top out about 12.5 knots, which isn't particularly fast. She's stable in a sense, but I'll talk a little bit about why that is, and that has some interesting implications on some of our survey issues. She's not particularly fuel efficient. You think, boy, look at those tiny little hulls. It must be just zipping through the water like a lightweight, one of those pontoon boats that you drive around on lakes, right? This is not a pontoon boat. And this picture, this just a couple of seconds later, gives you an idea of that. I mean, she's pulling a pretty big weight. We're going a little over 10 knots here, going through the canal. I don't know if we're violating some no wake zone rule here, but the idea here is this is not a small boat, right? And We're not a lightweight boat, and we're not particularly fast. So that's a pretty sizable wake. And why that is, here's a shot of her out of the water. So that is one goofy looking ship. So this is a picture in dry dock from last spring, where here's the white parts are above the water, red parts are below the water normally. And we've got these two big hulls underwater that are just connected with the narrow struts to the main surface. So that's the essence of a SWATH design. So SWATH stands for shallow waterplane, small waterplane, twin hull. And I'll draw a picture here to help tease that out, because it took me I got it when the first time I thought about it, but then the more and more we thought about it and had to deal with some of these issues. And maybe I'm just slow on the uptake, and you guys have it already, but of why that's a good idea or why it's not. So some other goofy things that I'll touch on here. So we've got a big bulbous bow here on either side, well down beneath the surface, unlike a traditional bulbous bow on say a container ship. These hulls, I'm going to show a couple more pictures so you get a sense of what the hulls look like, but they look like flattened, long, tapered cigars stuck on the bottom. Well, they are the ship. We've got stabilizer fins. You can see the aft ones, they're fixed, and the forward ones, they've got a fixed angle of attack. You can see there to keep the bow up. SWATHs have a tendency to nosedive at speed. There's not a lot of stability in the pitch direction. Not actually a lot of stability all around. I'll get to that. So SWATHs have a tendency to nosedive. So these are fixed at a bow up angle of attack, and we also have controllable trim tabs on the back of these things. I think some SWATHs, the SWATHs in the, I don't know what the class is. Do you know that the Navy operates for their surveillance ships? I believe they don't even have rudders. That's how they steer the things, is with these canards. Here's a view a little closer in. You can see the articulating surface on the back of the forward trim tab. You can get a sense of the shape of those underwater hulls. There's the aft control surface. You can just see the propeller glancing out. And these here are the buoyancy appendages, which is another odd thing about this ship. She came in a little heavy. One of her problems in the yard was, as with many ships, she came in about 20 tons too heavy. Turns out that SWATHs are very, very susceptible to loading, and so that was a problem. So rather than take weight off, which is hard once you've built the boat, last spring we added buoyancy, put water wings on them. Right? So these things are fiberglass, they're foam filled, they're pretty big, probably about 6 feet long. There's about 40 of them in total, and they're just bolted onto the hull, so they're submerged. They do float. The yard manager who was putting these on, a crusty old fellow who went by the name of Copperhead, down in the yard, in Kiwanis Yard in Norfolk. We was pulling them off the truck. He said, "You sure these things float?" I said, "Well, they're supposed to." Yeah, he didn't quite believe it, so he took one, he picked it up by the crane, dropped it in the water, and it did, in fact, float. So he was happy after that. Copperhead is a man who believes what he sees. So these are the buoyancy appendages, and I'll get back to those too. And here's a view from the stern. So we've got two propellers. There's an engine in each hull, a generator in each hull. So we turn a fixed 5-bladed propeller through our standard clutch reduction gear. So very maneuverable at low speed. We've got big rudders hanging behind. Very powerful at low speed. Clutch ahead's about 5 knots. And incredibly maneuverable. We can just spin around in circles, and she drives a bit like a skid steer, or what I imagine a tank would drive like. So a goofy looking ship. So here's a schematic of the ship looking fore and aft, and that gives you a cross-sectional view of what those hulls look like. And here's the small waterplane. Waterplane being the area of the hull that's at the water level. And so to think about this, of why you want a design like this, if you think of the ride of a very, very shallow, light, flat-bottom boat like a Chesapeake skiff or a Boston whaler, for instance, those are very light boats. They've got very large waterplanes. When a wave comes along, that acts on the waterplane. Basically, if you submerged 6 inches of that boat and stick it underwater, that's the force. Is that area times the times the distance that you're submerged, right? That's additional displacement. That's an extra force going up. Or similarly, if that boat comes out of the water by 6 inches, right? It's that area. It's the area. It's the heave measurement times the water plane area. That's the force acting on that vessel, either up or down. So anyone who's ridden a Boston whaler at moderate to high speeds through some chop knows that those forces get pretty big, and accelerations in the vertical direction get huge. Conversely, if you had and the key to the accelerations that you're experiencing is the ratio of that water plane area to the submerged volume, right? To the displacement, because the submerged volume is the weight of the ship, right? Thank you, Archimedes. So if I draw so a barge, for instance, lightly loaded versus a barge, that same barge very heavily laden. The water plane area is the same, but the mass of this one's a lot different. So we intuitively know that, right? It's heavier. It's going to tend to cruise through things. But why that is because, right, this mass, the force acting on these two when a wave comes along is the same, but the mass of this thing's gone way up. So the acceleration that this guy experiences is way down. Right, so that's all nice. So what can you do, and why do we care? Why we care is motion in survey platforms is bad, right? We want a sensor that cruises along without a lot of heave, pitch, and roll, because those things are hard to measure and they tend to flex things, and so we can either measure them very accurately or we can get rid of them. So ideally, you get rid of them by going away, right? Take a displacement hull, sink it underwater, and turn it into a submarine, which are great for surveying, right? Nice stable ride once you get away from the surface, right? They're a little rolly, from what I hear, on the surface because they don't have a lot of form stability that way. But you run into problems with positioning, right? They're expensive, et cetera, et cetera. So what if you just took a submarine hull that rides, just take a very narrow stick up through the surface of the water and then put your ship on top of it, right? So this thing it'll ride like a submarine, but you'll have the surface, the advantages of a surface ship. You get to breathe the outside air. You can put GPS antennas on it, all the rest of it. Problem with this is if you build a big ship on top of a little submarine like this, the thing flips over. So if you build 2 of them, you can build a ship that looks remarkably like the Hassler. So that's the idea of a SWATH, is to take the main displacement of the hull and get it away from the surface so your water plane's small. And it works. The ride on the ship is unbelievable, up to a certain stage. We just tend to cruise on through the water. Where it gets bad, as you might imagine, is when this is no longer above the surface of the water. So once we start putting the bow or the deck into the sea state, and that happens at about a 9, depending on the steepness of the sea, at about 9 to 10 foot. And then we start slamming into the waves. The ride quality goes down. It gets very loud inside the ship. The berthing is right above here. These are staterooms, so you're 5 feet away from steel slamming into a flat piece of metal, and that's time to call it quits. But for the size of ship this is, 124 foot ship, that's pretty good weather. That's pretty good weather ability for coastal surveying. I think that was one of the big motivations of going with the SWATH design, especially considering the NOAA ship Rudy, which this ship effectively replaced. That really, I think, looked more like that. It was a flat bottom boat built for a different purpose, but the ride quality, from what I hear, I never sailed on her, was not that good when the waves came up. So that's why you have a SWATH. And from a ship perspective, what that means is this ship actually has very poor stability. Stability in a ship construction sense being the ability of a ship to right itself from some small displacement. Right? So if we put a big weight over here, this ship goes brink, because there's not a lot of additional reserve buoyancy to counteract that. So she's got very, very low stability, which is how you get a steady ride. That's true in general in ships. A very stiff ship will have a very snappy ride, where one with the low stability will tend to just sort of wallow our way through. But this, by design, has a very low stability. So it has a couple of issues. It makes it very, very sensitive to weight. So when the shipyard said, hey, sorry, man, I'm 20 tons overweight, that's a big problem. That probably wouldn't be a problem on a non-SWATH ship. It makes us very sensitive to loading. If we take on fuel, down we go into the water, far more than you would on a typical ship, which makes the traditional surveying to the water surface, when we tidally correct everything, so we need to reduce all our measurements to a waterline, effective waterline measurement by taking out draft and dynamic draft and all the rest of those goodies, and then applying some either measured or predicted tide. That means you have to control your waterline, either by measuring it or actively ballast. We actively ballast at least once a day to make sure we're where we should be. So that's a bit of a bother. Also, going from density changes, going from saltwater to freshwater, if we go from fully freshwater to fully saltwater, we'll pop up by about 15 centimeters. So it's very sensitive to the density of the water as well as to loadings on deck. And trim-wise as well. As we take showers and fill up our gray water tank that's over on this side, the ship will start to flop over on our port sides. So it wouldn't be a presentation without a DTM. So here's so that's the ship, and I'll come back to a couple of other issues that come from making that decision to have a SWATH design, which solves your weather window problem, but introduces a couple of other considerations. So here's just where we've been working up here. We did a couple of years of work off of Norfolk and the approaches to Chesapeake Bay. But this is, so here's the Isle of Shoals. These areas in light green are areas we did last year, and these ones we'll be doing here, possibly here in the coming month. And then at a much smaller scale view, here's that stuff we did last year with some other contract survey and then some inshore survey work that both the TJ and the summer hydro classes here did. So we're junctioning with the summer hydro class work out by the Isle of Shoals. So that was pretty fun, junctioning with a survey that I...
Junction okay?
Yeah, junction was good actually, which is good because I was part of that survey and I'm part of that survey, so I'd have some explaining to do if it didn't. So instruments. Here's just a quick picture of some of the instruments we have on board. We have two hulls, so you might as well have two multi-beams. So we have two 7125s, one in each hull, and I'll talk a little bit more about those. So here they are. This is just a picture. So they're right up on the bottom of the hull in the flat of it, recessed a bit. This is an old one. We've since replaced that receiver. That's fresh from Mississippi. She's a little green. So with the 400 kilohertz transmitter and the receiver, so recessed into a pocket. Tom, you look a little concerned there. Do you have a question?
That's my natural look.
Okay.
Actually, I did have a question. You only have 400, you don't have the 200 on there?
We do now because we've put on the broadband, but we only have the one transmitter. So yes, we do.
And there's no issue with turbulence with that? I guess
Yeah, so this is flush with the base of the. I probably shouldn't stand in front of that. So this is flush with the against the receiver, and then by design, this face needs to be even with the face of the receiver. So this makes mounting 7125s a little tricky because you can't have this thing sticking out. So you need to have some sort of well to get that thing back up in there. So no, we haven't seen issues with turbulence. So we don't have a camera down there to look at it.
I mount them flat on the bottom of the hull and not on the outer surfaces of the hull too.
So they are angled slightly out. They're angled about 5 degrees out each side, and that was a series of calculations that was done on what optimizes your swath in different depths. And we've certainly done a lot of head scratching on. And particularly now that you have a lot more control of these sonars, you can steer beams that way, you can steer beams this way, you can do things that you couldn't do when this was envisioned 8 years ago. We have a 7111. Here's the going into shipyard. It sits in a little blister up on the starboard bow, so that's a 100 kilohertz system. There's me and my Sunday finest. We're doing a check of the offset survey in shipyard. And two Planex POS-MVs. Actually, we've since replaced these boxes with the new version 5s. And these are down. This is right down in the hull. That's the top of this. So this is well underwater, and the multibeam sitting right here. So the distance between the IMU and the multibeam is less than 2 meters. So that was intentional, and that was largely informed by the experience of the Creed, the Canadian Hydrographic Services SWATH vessel that I think you guys saw quite a bit of independent movement of the hulls, which is concerning from a ship driving perspective, right? Hopefully they, on average, come back together. So we've got 2 of them. And processing-wise, when the bulk of our work is done with the 7125s, we treat them as 2 independent vessels. They've each got their own POS, they've each got their own navigation solution, they've each got their own antenna set up above their respective hulls. It's 2 independent vessels that just happen to be always driving 15 meters apart. So that adds some overhead to the, it doubles everything that you need to do, particularly with positioning. But we haven't seen any flexing problems. I would hope not, right, with 2 meters between these, and it makes your offsets. You can be a lot more casual about your offsets, not that we are, with small lever arms. We do have this is a survey launch that's now scheduled to arrive next week. So small, 25-foot, much smaller than the boats that are on either the Thomas Jefferson or West Coast survey launches.
We're 24 feet.
What's that?
We're 24 feet on the West Coast.
28,
28, but who's counting?
Oh, you were?
but that's not bad.
Okay.
Well, it says 27, so I think it's 27 overall, but they're about half the weight. So they're much smaller boats, much different idea, and that was largely based on what we can carry. Obviously, a boat that's very weight sensitive can't go picking up gigantic survey launches. So this will be interesting. It's something we certainly need. A ship needs a boat, and we will outfit it with some survey equipment. Exactly what remains to be seen. We have a R2 Sonics 2022, the 2-degree system that we'll put in a recessed pocket in the hull. We also have pads on the hull so we can mount a side scan or any other miscellaneous gear. We also have we do tow side scan on occasion. We have a Klein 5000 version 2, so that's the side scan that also does the interferometric solution. We've looked at the interferometric solution a bit. We haven't done much work with it. We're towing it, which makes it kind of goofy. But if we get to a happier place with interferometric systems, we may stick it on the bottom of this for inshore hydrography. Here's the performance of the system. So here's just an extinction test we did just to give you an idea of where we can go and what we can survey. This we're off near Norfolk Canyon, just ran off the edge of the shelf collecting data. So here's the red is so the ship's up here. You can see the effect of the tilted head here a little bit. That accounts for the asymmetry. So here's our 400 kilohertz. The 200 kilohertz 7125 will get down to about a 400 meter swath in 300 meters. And then here's the 7111. So we can effectively survey probably down to 500, 600 meters, but anything beyond that's really pushing it. We have done a little work in those kind of depths. I did a collaborative project last year with the Okeanos Explorer, as well as the Henry Bigelow, in looking at some of the canyons, the heads of the canyons out in New York Bight. So performance. One of the good things about having these goofy shaped hulls is there's very little way for surface, either turbulence or wave action or bubbles, to get down underneath the hull. And they're down. The sonars are down deep, and they're well isolated from the propellers as well. So they're very quiet. Not that this. So this is a set of noise curves run at different speeds. So this is the speed in knots. So we're not even getting above the noise floor, and this is at a fixed depth of water. This is in about 20 meters of water until 6 knots. But even at full speed, we're only up about 7 dB above the quiescent noise floor. The asymmetry in here is because we're in the starboard. This is the starboard hull, so you hear noise from the port hull coming over more than you hear your own propeller noise because it's got a better bounce path.
What's that measured with?
This is just listening with the 7125. So this is just passive listening with the sonar at different speeds and then passing the data through by angle. So the water column, just looking at the water column and treating each beam as basically a directional hydrophone.
You control the water depth when you are doing this type of measurements because it's very sensitive.
Yeah, so this is over a flat seafloor,
Yeah.
and we've also done a series of tests in different depths of water, run the same line, same settings in different depths of water. And I don't have that here. This is something that we're trying to do a better job at. We don't currently I don't think in our fleet a real great job of understanding and controlling and monitoring the noise of our vessels, or just ambient interference into our sonars.
But this is with all ship systems on, compressors going, whatever you have on,
Yep.
normal operation.
This is normal operation. Now is that bad? Is it good? All right, I think it's good. 7 dB. What's 7 dB? So just when you have a great story, like I can explain the shape, then I process the data from the port side and it doesn't look anything like it. It's still small, the difference. These are completely uncalibrated systems, so these are just dB relative to something or other. The shape of it's completely different. They're still higher on the side towards the other side, but completely uncalibrated systems. So 2 holes does give you the opportunity to put a sonar in each one, and that sounds like a good idea. Because if you're working in shallow water, well, that gets you twice the data, so it gets you more coverage. In deep water, it doesn't make much of a difference, but in shallow water, it really does. It really boosts the efficiency of the system. So we, as originally installed, the system, Reson couldn't deliver on the promised dual ping setup, so we were trading pings back and forth. One system would ping, receive, and the other system would ping and receive. That's a really bad idea, and you shouldn't do it, in case you think about doing it in the future. So we can now ping with both systems at the same time. We're doing that through, or Reson's doing that through frequency modulation. So one head is chirping up, and the other head's chirping down. They're also separated in frequency space. So that didn't work that well in the beginning, and when I came in here, there was a bunch of FM chirp pulses on here, so hopefully, I think somebody's thinking about FM stuff, so that's good.
That was our class this morning.
Okay, good. So this was the original implementation of the FM as delivered, just as a cautionary tale. So here, this is the beam format. So this is beam number. So I've unwrapped the wedge display, and here's the seafloor that we're after, and this is the seafloor we're not after. This is the seafloor. This is the bottom bounce from the other head. So that's not good. And this is just a track down of taking the max. So trying to extract the echo level from the seafloor. And this is the signal we want, the green one, and the blue one is the signal we don't want. Obviously, these guys are very close together.
It looks red to me.
It's bad, right? Good, bad. So that is bad, and that was terrible because it gives you all sorts of, sort of what looks like a nadir ring off nadir, and so that was unsat. So we looked at more and working with Reson and helping them work through their code. They had some nasty bugs in there. Their match filter was coded wrong, so we were matching the wrong match filter to a transmit pulse, which actually gives you a depth bias, and that's really bad when you're out doing hydrography. So we worked through all that stuff, and this is these are the plots that Tom and Xavier looked over my shoulder and said, that ain't right. They didn't look like this. They looked much stranger than that. So here's what it looks like in frequency space. So here's frequency on this axis, It's just arbitrary dBs. And this is a completely synthetic pulse. I didn't put this in a tank. I have no idea what kind of weightings applied. So I just used a regular rectangular pulse with the frequency sweep that we use. So you could do fancy things with the side lobes by applying the weighting, but I haven't done any of that. So the point I want to get across here is these two signals from each head are separated both in frequency space and then some additional separation from the application of the match filter. I don't know much about match filters, so I didn't try and pretend what kind of separation you get from that. But the point here is as you shorten that pulse, as we're wont to do as hydrographers, because short pulses mean higher resolution, and higher resolution means better, you wind up decreasing the effective separation of these signals. So this is 0.3 of a millisecond pulse, a 1 millisecond pulse and a 10 millisecond pulse. So obviously, the longer the pulse you get, the lower your side lobes, and the more effective separation between the two signals. So we tested that. This is a bit of a mess of a plot, but the colors go together. So the blue is blue, and so this is actual data of the desired signal versus the interfering signal from the other head of 0.3 of a millisecond. Then the green is 0.6 of a millisecond. So you can see that under 1 millisecond, once we get the pulses too short, we start seeing a lot more interference. But over 1 millisecond, we're effectively separated, and we can't. It's down in the noise. So we run this system at 1 millisecond. Now that's not very scientific, but that's a field test of interference between two systems. So one thing about the having two hulls is we do have two IMUs, one in each hull down here. And one question is, well, do you need them? And are the hulls truly moving independently of each other? And if so, how much? So this is, I've been looking at this data, and there's nothing like a presentation to make you finish your code and look at your data. So I've been looking at this, and I finally gave up this morning. But this is the spectra of the attitude from a whole sheet out. This is surveys done in the fall on approaches to New York. So there's the roll is about 8 seconds. So this is frequency in hertz and dB. So it's a log plot. And then I was going to look at the difference between these two systems. Hey, I've got two position solutions. Why don't I look at the difference of them, and then I can see what's happening with my system. So I did that, and I got this cool looking plot, and I said, oh, isn't this awesome? The roll difference is really correlated with pitch. Who would have thought that? So I was coming up with all sorts of crazy, like every time we pitch down, the hulls splay out or something wacky. But it occurred to me I think yesterday, that wait a minute, I probably have crosstalk between my two reference frames, because my reference frames probably aren't exactly aligned, so I've got to go correct for that. So I don't believe this result quite yet. But that points to another issue is you got reference frames all over the place. Usually you have a reference frame of a sonar, or a reference frame, I'll use a right-handed system, reference frame of your IMU, and that's enough to deal with. In your patch testing, usually we throw in the reference frame of a ship just to confuse things. But now we've got double that. So we've got reference frames on both sides and the ship, and so the offset spreadsheet is a bit of a bear on the Hassler. So this is a picture I took last week as I was walking down Wentworth Road with my cell phone camera. It looks a bit like the Costa Concordia. So we're not aground. We have not run the ship aground. So this is an illustration of two things. One, how unstable the ship is. Just with moving ballast and fuel around, we can get the ship into this kind of trim. Right. So that's usually, if you see a ship doing that, that's a problem, right? But we're very, very sensitive to loading. Actually, the first time we ballasted like this, the Coast Guard came over, because the Coast Guard base is not 200 feet that way. A gaggle of those guys came over and said, we see you appear to be listing a little. Is there anything you need help with? So we probably should have called them ahead of time.
We got a call here too.
Yeah.
One of the neighbors.
I appreciated that he referred to it as your ship.
Yeah.
So what we're doing here is we're ballasting to get at those buoyancy appendages. So there's a guy working on them. There's divers in the water working on them. And what happened is we got a call in, I guess that was in November. We just pulled in, we were working in the Gulf of, in the New York Bight. Pulled in on Friday, everything was good, about to knock off for the weekend, and got a call from our PR guy down in DC, and he said, I just got off the phone with a woman from New Jersey, says she's found a piece of your ship. I said, well, that's kind of weird. So we gave her a call. She said, yeah, I found a piece of your ship. I said, what do you mean you found a piece of our ship? She said, well, it kind of looks like a scoop. I said, how do you know it's ours? She said, well, it says Ferdinand Hassler on it. I'm trying to think, well, what looks like a scoop that would have like a bailing bucket out of the rescue boat, or something the deckies threw overboard. So I said, could you send us a picture? She said, yeah, sure. So here's the picture. So it does in fact say no ship Ferdinand Hassler, buoyancy appendage, starboard hull, inboard number 2, this end forward. So we saw this picture and we knew we were in trouble. And there she is sitting on the beach in New Jersey, which is it's a pretty artful shot. So that gives you an idea of what they look like. So they're pretty big. So the town in New Jersey was great. I talked to the public works guy, and I should have written down his name, but he was terrific. He said, "Yeah, I'll go get it off the beach." And they went and picked it up off the beach and shipped it back to us. So it failed. Obviously, it came off. The bolts came unstuck. So we're working on how to prevent that from happening in the future. We didn't feel it. It's not like one of these things comes off and all of a sudden you're listing over to one side. I think the net buoyancy on one of these things is about on order of 1,000 pounds of buoyancy.
Amazing the shipyard had the wherewithal to predict it was going to fall off and put the name
and label them.
Yeah.
That's pretty good, isn't it? And it landed just the right way, so it didn't. Yeah, that's pretty good. I think this is because there's quite a few of these things. So just when they arrive on a pallet, it's like a jigsaw puzzle.
We
So
usually
anyway.
put our phone numbers on those things.
You get these little cards you tear off and stamp on them,
Uh-huh.
put it back in, Bobby with this.
Yeah, so we're going to try and stop that from happening again. So we're working on a bunch of different answers. So some other things we worked on. We did do a project last summer with an AEV. So this is NOAA's Remus 600. It's got a EM 3002 in the nose, so it can do multibeam bathymetry. So a team from HSTP came out. One of the challenges with the Hassler is we don't have a lot of berthing. We've got 14 bunks, and the crew takes up all those 14 bunks. So we don't have space for the AEV team to come on board with their 5 people and 3 graduate students and fiddle with the AEV. So we were working out of the off anchor in the Isle of Shoals and keeping a team ashore to spin this up, and then we went out for a full leg with what we need to run it. So once they got us up and started, so we just had a couple of people with us. So it was successful insofar as we got it back. We got data with it. And I don't think this video is going to play, so out of here. So I've got a video of this deployment. It's got sound, which I didn't know. Oh, there we go. So this is our current operations officer, Lieutenant Adam Reed. This guy had the good idea of putting a GoPro on this thing as we slung it over the side. So just as a background, to have a conversation about the AUV, AUVs, we like them and they're cool, and this one certainly is. But in terms of, and part of the NOAA's idea with this AUV and part of putting it on the Hassler, and I believe it's here now and it's going to live up here, is to figure out how to use these things for missions that we have. And certainly deep water missions, like the heads of the canyon stuff, this would be perfect for. High resolution down near the seabed. If there's stuff around here, dodging lobster boats, lobster traps, this may not be the right tool. So handling, the deck edge is pretty high up. Does that sound a little distracting? I don't know how to turn the sound down. It'll go underwater here. So we had to rig up ways of launching this thing. But our deck edge is kind of high up, which is part of the SWATH design. You need to have a high deck to give enough clearance, because that ultimately determines the sea state you can work in. that makes putting things over the side a little challenging. We've got that wonkin' big A-frame on the back, but even still, the clearance between the vehicle and the stern of the ship wasn't huge.
You have stability issues with heavy weights on the A-frame, with pitch?
No, I suppose heavy enough we would, but not so much that we notice it here. So this vehicle weighs about 600 pounds, I think, 600, 800 pounds. So AUVs, so they're, we're gonna do it again. We're looking forward to working with Val and the boot camp. I think that's all set up for this summer. So that'll be a good collaborative project. We certainly need to get better on both how to use these things reliably and also answering the question, what should we be using them for? And we're probably not going to use them for the same thing that we'd use the launch for, or that we'd use even some of our ships for today. It eventually goes on the water.
As long as we're waiting for it.
It looks like when you fall overboard.
Yeah, the ship gets small real quick. So some other things we're working on. Well, so just to continue on the AUV, so autonomous is good because it doesn't have people, but AUVs usually come with a team of people, and we don't have berths for them. So as long as we can do that. It goes underwater and then comes back, so it'll probably go quiet for a while. So maybe an AUV isn't the answer, or answer for everything that we're looking for, but maybe autonomous surface vehicles. Maybe if we could get that launch to drive itself, or to station keep, say 50 meters off our starboard quarter like a well-behaved dog, and fall in when we see something. Maybe that would be more effective. So that's some operational things that we've been kicking around. Another issue we get from the limited berthing is keeping up with acquiring and processing data is a bit of a bear. We've got one survey tech and one rotating physical scientist, each of whom spends a 12-hour straight watch. 12 hours straight acquiring and processing data, and then a couple other people rotating through there to help with the planning and the processing. So we don't have a lot of slack to absorb debugging problems, writing fancy reports and whatnot, so we're going to quickly get behind with a full schedule. So one thing we're looking at this year is remote processing of data. We have rather than shipping the data off or having someone send data off, process it, send it back, we're working on just having someone remote desktop into our system and process data using our processors, our computers, but they're just passing the control. That runs into a couple of interesting problems. Normal shipboard internet's VSAT. VSAT goes through geostationary satellites. Geostationary satellites have about a half-second delay by the time you go up and down and back again. So controlling a mouse is pretty much impossible. Do you run into these problems with the Okeanis? With people? Do people actually remote drive or remote process stuff? Or?
We've tried, but it was for fun. We never really actively tested it.
Yeah, the latency is tricky, and the bandwidth issues as well. So we've installed some 4G systems, so hopefully when we're operating close to land, we can just use a 4G connection. Some other things we've been working on is sonar. Sonar health. Are our sonars good? Is this thing broken? I know this is an area of interest of a bunch of folks here. So this is an example of a bad sonar. This is a 7125, an old broken one. And so I've been working with Glenn and some other folks on, right, here's frequency count. Well, I'll just show you that. This is a bad one. This is a good one, right? Good, bad, good, bad. You can sort of see why it's bad. But this is an element look. That's a frequency look. This is what happens when I mess with the gain look. And this is sort of just a water column noise look. So, I was looking through. We spent a lot of time in looking at backscatter and backscatter processing and normalization. That's good, but what the hydrographer cares about is bottom detections. So we goofed around a little. This is an old slide of mine of success rate. What if I mess around with different settings for a given seafloor? When do I get good detections versus bad detections? So obviously this is a bit of an iterative process. You need to know what a good seafloor is. But here, this is by, so the red, the deep red is 90% success rate. This is down at 10%, but you can see that, you know, there's obviously a sweet spot here in the middle. So that's an idea like, okay, how should I operate my sonar to maximize bathymetry? Backscatter, how might I do it for bathymetry as well? And this is largely into response to breeze. Say?
Is that a 7125 settings?
This one? Yeah, power.
Seems like a lot better gain than I would usually use with lower. I don't know. It's not within the ideal settings. There don't look like they're within the.
So this is TVG off. So you gotta back out your TVG curves. So this is total gain applied. Yes, that's kind of interesting, right? So just in terms of quantifying how we should run these sonars, and this is largely in response to Tom, I think your desire to see a before and after shot for backscatter. So we've been working on normalizing backscatter between different systems. So we presented a paper at US Hydro last year. This is something that's interesting to do but we have to do it because we've got two systems always running around right next to each other that usually do not have the same dB offset between them. So this is a before and this is an after. And that may not look so much better, but the image dynamic range is 10 dB lower. This is 25 dB dynamic range, this is a 15 dB dynamic range. So we've actually done quite a bit of improvement between the two systems.
It's different between the top half and the bottom half.
This one?
Did you get, yeah.
Yeah, it still is a little bit, that's true.
No, like back a picture. Yeah. Like
Yeah, so these are different run days. So the sonar was turned off and turned on, and it turns out
Same sonar?
Same sonar. Well, so you see two sonars here. You can see there's starboard head and port head overlapping almost 100% in this case. And this is a different day. We've gone in, we've turned off our sonars, we've come out again. So yes.
Same settings?
Probably not the exact same settings, but pretty close. What we found is there's big gain offsets between different initializations of the system.
This is the calibration routine it runs at the beginning of the day?
Yeah, so we've stopped doing that. But you still, this would be the same thing you'd see between, say, launch RA4 and
2805 and
RA5.
2806.
So we've been looking at different techniques of fixing that problem. So that's all I had for slides, so I'd be happy to take any questions.
And then in the very last slide, what were we looking at? What was the?
Where?
Where and what?
Okay, so this is acoustic backscatter from a 400 kilohertz system. This is off the approaches to Chesapeake Bay. So this is probably about 30 miles east of Cape Charles. So these are, so whiter is higher acoustic returns. So we've taken bottom samples. So we use this to guide our bottom sampling. This is a fine green sand. This is a coarser yellowy sand with shell hash mixed in some of the places. Anyway, and this is a little shallower here, and you can see these are moving dunes. So that's kind of cool. Yeah.
Just to follow up on that when you turn it on, it does the compensation thing.
Mm-hmm.
Does that become something in your fleet of 15 of these systems? Is there a standard practice to not do that, or are you still sorting that out? Or
I don't know. We've certainly turned ours off, but you have to go in and monkey around with the XML file.
Right.
You certainly should.
Do some versions do it automatically and some don't, but Glenn just instructed everyone to disable the auto normalization.
So like that's a message in the field procedures workshop,
yeah,
don't do this.
but they're going to normalize at each new project location, and they're going to save the files.
You know what the system is trying to do when it's doing this?
I think it's trying to normalize so you can apply the right element weighting and get good beamforming. You need to so if there's any slight gain offsets between the elements, that would corrupt your beam pattern. So it's just trying to measure them and then stamp them back down to the right weighting level.
Yeah, just keep the sidewalls from popping up. But it seems like the 8000 series always did this too. You could actually watch it. It looked like a little equalizer thing. But for some reason, it seems like they sort of, in doing this, have lost our reference and it wanders around or something. Something that, I don't know if you, I'm sure they know of this, but.
They do.
Do you see any effect in the side load levels or bottom detections? I mean, are they noticeably improving things and you're making it worse by not doing this normalization?
Oh, we haven't looked. That's a tricky measurement to make in the field, the side lobe levels. We've goofed around with it a bit, you know, looking at the nadir ring, but it's versus the, just trying to find that nadir ring and looking at it and trying to get your side lobe levels, or putting other targets down there. But we don't as a practice make that measurement. We probably should, and that may be something to roll into, an evaluation both of, is this sonar good enough to use and is it going bad? Which are two questions that are always in the back of a hydrographer's mind. That would be a good one to add to the tests, to some level of side lobes. Tom?
Your plot that had the color map of when you got good bottom detections?
That one?
Yeah, if you were to draw your saturation curve on there, do you have an idea about where it would fall, the backscatter saturation curve?
Well, my guess is you're tailing off right here.
On the upper edge of the red?
Well, somewhere in there.
Somewhere in there.
Probably down here, actually, is my guess. These systems get curiously good bathymetry in a completely railed state, which I've never understood.
So it's not there's always this question of the either or. Can you get good backscatter and get good bathymetry? And it seems like it'd be nice to couple those together.
Yep.
It seems like the jury is still a little bit out on that. I've heard anecdotally mixed stories that when the Glenn Rice's saturation monitor is run, sometimes it makes much better bathymetry, and sometimes if the conditions are tough, maybe up in Alaska or something like that, they get left there less successful.
I know the Fairweather is that's a very active, top priority thing for us this year. We haven't had the hardware to support running the SatMon tool, just because all of the launch computers didn't have the memory to be able to run SatMon and collect bathymetry with HIPAC and everything. But just now, it's been out for a couple of years, and we're just going to actively start looking at that on our ship this year. So we're finally new computered up and ready to go.
So stay tuned.
Yeah, on Rainier, we've been running it for the last couple of years, and my experience, at least, is that most of the time you can run especially once you kind of learn how to tune it in a SatMon regime. You can run keeping it not saturated. There are certain conditions where the bathymetry suffers, and so there is that trade-off. Most of the time, if you know what you're doing, I would say but there are also a lot of resistance to people who just don't like it and have traditional.
Well, and they're good. The field hydrographers pick the guys who are sitting in front of a sonar with knobs to twiddle all day are often surprisingly good at finding the nut. Right? Some of them aren't, but a lot of them are. So it's yeah.
Yeah, I was curious. Come back to your two-hull situation and the FM sweeps that you're using up and down and frequency separation. You clearly demonstrated that you need to get at least to a millisecond pulse length before you start seeing that separation, which makes perfect sense. Why can't you go beyond? I mean, you said the attitude, well, the shorter the pulse, the better. Well, that's not necessarily true in a chirp mode, in a match filter world. The longer may be much better, and you may be able to keep gain levels at a very reasonable level and just make up for it by time bandwidth product.
That's true. What I believe, Xavier, stop me if I start going down a bad path here. I believe with a longer pulse, you're more susceptible to Doppler shift problems.
Yes, that's probably true.
So I think it's a.
I don't know in the water depth you work whether that's going to be serious, but.
No, nor with the accelerations that we see or the velocities that we see. We really don't move that much, so that may not be a problem. It seems to work, so that's why I'm putting it up there as an area for. I don't know, it seems to work to us. I mean, but does that mean it's the right thing to do? I don't know. I know Eric Maillard's put out a paper on the right settings in different conditions for pulse length and bandwidth in an FM pulse. But it's certainly nothing that we have a lot of knowledge out in and we're getting more and more of these FM systems, so it's probably something we should be thinking about a little more.
It may come around to start addressing some of these saturation issues too, because again, if you can keep the power level low and just increase the energy output by making the pulse longer, if the match filter is working, you might get the best of both worlds.
Yep. Yeah, it could be. What else? Or we could get systems with bigger dynamic range, right? Which is, I think, something we need to corporately realize and probably start asking for. Okay. Xavier.
Do you apply some particular processing for the data that comes from the overlapping part of the SWATH? In comparison with what is being done, presumably, classically, on the outer parts of it?
No, and you can see we just grid it all up. If this shows, well, this probably shows better. Once you get into deeper water, you wind up with a lot of overlap between the two swaths. I think we get, boy, if Mr. Kidd were here, I had him do this math yesterday, but I forget the answer. But it's at a certain depth, in really shallow water, right, we get a gap between the two swaths. But starting at something like 5 meters underneath the hull or so, and down we get coverage, and then in deeper water you get almost 80-90% overlapping coverage. So we dump them all into the same hopper and just grid them all. So overlapping swaths, the two hulls.
Because for bathymetry, this increases the number of soundings, which is good. Basically.
Yep.
But for reflectivity, you get data from different angles.
Yep.
For a given point of the seafloor, so the reflectivity should be different.
Yes.
And you mixed them all the same?
No, so backscatter processing, we treat each head independently.
Okay.
So when we process the backscatter, again, we're processing it as two independent vessels. And then only doing these normalization steps currently at the very last stage to try and normalize these. So this is what Brady?
No, go ahead.
So you could conceivably, right? That's a neat measurement that you're making, right? You're making measurements. You're making a bistatic measurement as well as two monostatic measurements from different. I mean, you could probably do a bunch of real neat analysis with it, but no, we don't. We just lump all the bathymetry together and then treat the backscatter independently. Yeah.
Two questions. One kind of a follow-on to Xavier's. Well, actually, I'll ask the other one first. You mentioned having to do waterline measurements daily.
Yep.
Have you tried any of what Glenn Rice calls ERZT or EZTR?
Yeah, we have. We have been trying our darndest to bag the waterline entirely and just survey the ellipsoid, because that would make our lives a lot easier. Right? We don't have to ballast every day, just as long as the ship's not going to tip over. We don't have to worry about tide gauges. So we've been very actively going for all ERS solutions all the time. It's proved harder to do than we had expected. We've been using, so this is using, I think Tom, we've talked about this as well, just the robustness of the solutions. It works most of the time, but when you're 24 hours a day for months at a time, it's a lot of data, and even a bunch of hiccups create a lot of processing, manual processing overhead. We have discovered fairly recently that our Iridium phone interferes with our GPS. We get big cycle slips from our Iridium phone. So,
Some of the aircraft avionics interfere.
and that made us all feel pretty dumb, because we've been scratching our head at this for 2 years. And once you look at the problem in the right way, and Dave Muller, survey tech, said, "Watch this." Put the there I am watching the cycle slip display on the POS-MV real-time controller. Made a Iridium call with the phone, and all of them go slip, 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 slip. And you can see in some of the data all the cycle slips just all together. So my brutish answer to that was, all right, that's it for the Iridium phone. But I think we're working on that.
That's a good XO answer.
Yeah. No more calls to your girlfriend. That's it. But we're looking at some different options. Can we filter the Iridium signal? Can we filter the GPS signals to eliminate that interference? But yeah, we'd love to be on the ellipsoid and not worry about the water line whatsoever.
Did you try moving the antenna around? What was the proximity to the GPS antenna?
It probably is, but there's only so many places we can put it.
I just wondered how close.
We just discovered this about a month ago, so we're not. We haven't figured it. It's not.
It's about as far as you can get looking at that report that he put together, because
Yeah.
the GPS antennas are on kind of the upper deck, the top of the deck house, and then the iridium antenna is way up on about as high as you can get on the mast. So
Yeah.
not only is it above, it's about
We
as
see
far as you can
cycle
get away.
slips too sometimes that we just don't know where they're coming from.
Yeah.
I just didn't know how close you needed to be.
Yeah, it's a challenge. Yeah, probably can take one. Can I take one more question?
Yeah, so I had one more, and it was, again, related to Xavier's question or comment. It seems like having essentially two different ships with the two different hulls, two different IMUs, two different navigation solutions, two different sonars, gives you a lot of redundancy, which is a good thing in surveying. It provides opportunities for not only getting maybe statistically optimal solutions, but just doing some good calibration and validation. For example, it seems like one thing you could do is maybe develop some automated tools to put your two navigation solutions into some kind of checker. And you need to know the positional and orientational offsets, but if you could throw those two navigation solutions into something that just sends something back and says, yes, these agree to the level we would expect, or no, they don't.
Yep, and we do as part of our normal quality control check on these is a difference between the two, a nav diff difference, and just look at it and see if one's gone more than reasonably off from the other. But yeah, we can certainly do a lot more on that time, and that's what I was trying to do earlier this week until I ran out of the limits of my both procrastination and programming ability. Yeah.
I was just wondering, in a general sense, do you think it has benefits? What are the pros and cons versus a more traditional hull design?
Yeah, so to bring it back home where I said I would and probably didn't. So the benefits is the motion in a sea state. So typical coastal sea states of, right, 5 to 10, well, it's usually not 5 to 10, right? 4 to 8 foot seas. What you'd see most of the summer, spring, and fall in coastal waters of the eastern United States. The platform is incredibly stable. Very smooth ride, great data quality. The sonars are down deep. Never seen bubble sweep down with the system. Never see, they're 12.5 feet down, so you really don't see aeration from the waves. So that's an advantage of it. Disadvantage of the SWATH hull is it's deep. So 12.5 feet is kind of a deep draft for a little boat. So that with our transducers that deep, we can't really survey very effectively in shallow water, right? Because you're losing all that. You're losing 4 meters of potential water column where you'd rather be higher up in the water. So I think that's the one place where it will be good to have a small boat is because the small boat sensor is up higher in the water column. So to do further inshore, our efficiency really goes downhill when we get into shallow water. That also the depth of the hull and the propellers, which is good for stability and a data quality standpoint, also makes towing side scan pretty tricky. We've got to get the side scan fairly deep to get it below the prop wash and below our wake. So we can't really tow side scan effectively in shallow water and maintain the specified height off the seafloor. So really there's very little, there's almost no conditions where it's more efficient to tow side scan with this ship than run multibeam, which is not the case with others. So that's an interesting trade-off that I don't think we'd really expected. So.
Do you guys have a big depressor wing, like for your 5,000?
We do.
You do, and even with that, you can't have trouble?
No, we can get it deep, but then it's too close to the seafloor.
Oh, but it's
so we need to get it below the wake,
Oh.
and then once it's below the wake, it's too close to the seafloor, so you need to lower your range scale. So, yeah.
Who's gonna drive those small boats? You don't have
Robots?
people. Like, are you gonna just borrow grad students until you get the robots to drive it?
Yeah, so that's tricky, right? So and the answer is we cannot sustain with our current model 24-hour ship ops plus running that small boat in any sort of operational way. Just can't do it. Now we might in the future if say we can get someone off the boat who's currently on the boat. Right? Can we kick the ET off permanently? Can he do his stuff from shore? Do we really need a processor? Do we need someone to attend? Do we really need someone sitting there watching the acquisition in real time? Do we even need someone at all, or could that be done remotely? If we can do this stuff remotely, and you start with the premise of the boat only works in inshore waters, can the boat have a 4G antenna and the sonars be operated, if they need to be operated, by someone sitting somewhere else?
Do you have an engineering watch all the time, or no?
We currently do. We're a watch standing boat. Boat's built to be unattended engine room, and we hope to be getting to that this summer. Now, does that mean you get to get rid of an engineer? Not currently, but long term it may, that you can offload some of that other effort.
I realize there are stability issues, but is there any hope of a berthing van added?
Yeah, so there's pads for a 20-foot container. We have to take the davit off. So where the davit can come off and a berthing container can go on. We've got all the hookups. Do you know who's got one?
Yeah.
So yes, we do have that idea.
Microwave dinners?
Yeah, you could. So you could go like the tugboats, right? And everyone cooks their own dinner. I don't think, if any of my wage mariners are listening, we're not going to do that.
Call my union.
Yeah, so there's different, but as we're currently configured and as we currently think about surveying, we couldn't do it. Now, it doesn't mean it's not useful, right? If you have a project area like around the Isle of Shoals that has an inshore area, it may make sense to survey, anchor the ship for a couple of days and do the inshore areas and catch up on survey. So it's not that it's going to be useless, but we certainly don't have the manpower to run launch ops.
Have you considered a trailing alongshore party?
No, in the Rudy sense that you have a trailer and a.
Yeah, the Farrell used to operate that way.
Yeah, or in conjunction with an NRT.
Right.
That's a model we poked at on the West Coast in Bellingham Bay. Yeah, so it's a different operational model that we're going to have to think of. We can't just pour on the people like we do on some of the other boats. Okay, so I've gone over, but yeah.
Can you operate the MVP sensor altogether with the side scan?
Yes. Yep. Yeah, and that's one good thing about having a ship that's so wide. It is the widest ship in NOAA's fleet. It's wider than the Ron Brown. Is we get quite a bit of separation between the stuff that we're towing off this turn. So we try not to turn when the MVP's down, but you try not to do that anyway. But yeah, you could, I think I tried to tangle them and you couldn't.
Fairweather tows MVP and side scan at the same time as well, and we're much narrower.
Yeah.
You just don't release the MVP when you're turning.
Right, which is usually a bad idea.
Yep.
Yeah.
So just two questions. Just,
sure.
I think we commented was, you're working 24-hour ops mostly, is it?
Yep.
That's what the goal is to
yep.
do that. Okay. Second question, with the dual systems and the acquisition of the data, are you running two instances of HiPAC, or is this totally, you're integrating them into one?
So we're actually logging all the data in the Reson boxes in the S7K format. Okay. So we use HiPAC just to drive lines, but we don't log data in it.
Okay.
Which hull drives the line?
That has been the subject of many a discussion. And when you're doing a patch test, which hull drives the line? So the answer is we drive the line at the center of the ship when we're doing two-hull operation. We drive it on. If we've turned one off, we drive the line with the hull. And in shallow water patch tests, we patch each hull independently. So you drive the lines with offset. It gets confusing real quick. All right, now I've gone 10 minutes over, so I should probably go. So thank you all, and please stop by sometime.